Hi everyone, I am Niranjan. I am a graduate student at UC Merced with Professor Ajay Gopinathan. And we do Brownian dynamics model of intracellular cargo transport by teams of kinesin motors. And we look at the effect of the lipid membrane enclosing the cargo on multi-kinesin transport. You might be familiar with this animation of a single kinesin carrying an intracellular cargo. In cell, however, typically a single cargo is carried by multiple motors working together. And the team sizes can vary from 2 to even hundreds of motors. Such multi-motor function is necessary to carry cargo over long distances through crowded cellular medium. Based on this importance, a lot of work has been done to understand how single motor as well as multi-motors work together. Some typical approaches that are used are optical trap-based experiments and also gliding assay type experiments where microtubules glide on top of motors, and interesting approaches like membrane tube extraction from vesicles by teams of motors. Such experiments have generated a lot of interesting results. One result I want to highlight here is that when kinesin motors were coupled to each other through an elastic cargo or rigid-like cargo like DNA, they did not work together well. When they independently step, they generate tension between them, and because of that, there is enhanced detachment of motors from the microtubule and lower run length. Run length is the average distance traveled by cargo. This interference is very significant, about almost 50% of decrease in processivity when they function in group of 5. That brings us to a question: how do teams of kinesins work together well in cargo and transport over long distances? In general, if we have a difficult job that is to be done, either we can recruit more people to the job, or we can make existing smaller teams more cooperative. We show using Brownian dynamic simulations that the lipid membrane that is enclosing most of intracellular cargoes helps in achieving both recruiting more motors as well as making motor teams more cooperative. In flat membrane geometry, there is already evidence that when you distribute kinesins uniformly, over time, the kinesins can diffuse and accumulate on the microtubule. But in cell, we have spherical cargo geometry, and also there is motor binding as well as motor unbinding. So it remains to be seen if in spherical geometry does the membrane help in increasing availability of motors. And also, there are reasons to believe that membrane might be helping in to make motors more cooperative. Consider this cartoon. In rigid cargo, when the motors develop tension, there is no way that they can relax the tension. Whereas if they are in membrane, when one motor experiences tension, it can slightly relocate and reduce some of its tension. We can test these possibilities directly in experiments like transport of membrane-bound cargo transport. Such experiments have generated interesting but some conflicting results. In small teams of kinesins, it was seen that both rigid and lipid cargoes have same run length, whereas in teams of myosins, lipid cargoes had higher run length. We wanted to develop a Brownian dynamic simulation to answer all these questions. First, check if the membrane increases availability of motors. Second, check if membrane changes intermotor interference. And finally, explain the conflicting run length results. Our model builds on earlier works on modeling multimotor transport. Very early works consider mean field approach, where all motors share equal cargo load. Later improvement was to consider unequal load sharing, and that explained experimental results better. And next improvement was to consider a three-dimensional cargo surface. And only recently, full 3D simulation with the motors diffusing on the surface has been developed by a group in Irvine. Our model is very similar to this model, except that the focus of our work is more on intermotor interference, whereas this study looked at availability of motors and how that changes run length and binding time. And also in our model, we changed the ATP concentration in the medium, which is found to be an important parameter. A brief explanation of our model: cargo is a sphere and motors diffuse on the surface. And when they come close to the microtubule, they bind to the microtubule. Bound motors are shown in blue. They move on the microtubule, and also they can detach. Both of these processes are dependent on the force that the motors experience. Center of mass of cargo follows this overdamped Langevin equation, where F is total external force on the cargo, which includes motor forces as well as steric force from microtubule. Gamma is friction coefficient, which depends on viscosity of medium, and eta vector is thermal noise. As I said earlier, we take into account ATP concentration. As we lower the ATP concentration, both the single motor velocity as well as the single motor detachment rate decreases. First, we looked with this model how the membrane changes intermotor interference. Here you see force correlation, which is the product of X component of motor forces when they are in teams. In rigid cargo with the motor diffusion constant 0, the force correlation is negative, which means that motors are likely to be located opposite to each other and they pull on each other. In lipid cargo, this force correlation is almost 0, meaning the membrane reduces intermotor interference. To confirm this, we plotted the force distribution of single motors in rigid and lipid cargos. Again, we can see that lipid membrane reduces force experienced by motors. Thus, membrane reduces negative interference, and that then leads to lower detachment rate of motors from the microtubule, which means that motors on lipid cargo survive longer. Next, we looked at how it changes the availability of motors. Here you see both rigid and lipid cargos start with the same number of motors, and over time, lipid cargos accumulate higher number of motors than rigid. We thought that this reduction in negative interference and then increased availability of motors may lead to higher run length or average distance traveled by cargo. And we measured that in simulations for saturating ATP conditions and small teams of kinesins, but we did not see any change in run length. Actually, this result is in agreement with the experiment on small teams of kinesins at saturating ATP conditions. Then we realized that if we change some parameters, like if we change the ATP concentration or if we change the number of motors on the cargo, for some parameter regimes, in particular, when you decrease the ATP concentration, the run length increases with cargo surface fluidity. And this is in agreement with the experiments on teams of myosins. So our model reproduces the experimental results of increase as well as no change in run length. Finally, we looked at other interesting cases that are relevant for experiments, motor teams in the presence of external load. First, in the presence of a hindering load, we see that motor teams in rigid lipid cargos dynamically cluster at the front end of the cargo. Such clustering is not possible in rigid cargo. Then we placed the cargo under a model of optical trap, and we measured collective forces generated by motors in lipid versus rigid. And we measured for different values of single motor parameters. This varying single motor parameter here is a proxy for exploring different motor types. We see that for most part of this parameter space, the lipid cargos, motor teams in lipid cargos generate higher collective force. In summary, fluid surfaces of cellular cargo reduce mechanical interference, increase availability of motors, thereby increasing the distance over which they carry cargo. In future, we are now applying the model to more physiologically relevant scenarios like roadblocks on the cargo path, heterogeneity in motor properties, etc. And also we want to compare it with in vitro as well as in vivo experiments. With that, I thank my advisor, Professor Ajay Gopinathan, and all my lab members at UC Merced. And thank you for the opportunity, and thanks for listening.